Continuing our discussion of electrical systems, we're going to talk about electrical potential. Now, before we discuss electric potential in detail, let's have a bit of a recap about what potential really means. Potential energy can be a number of things. It can be chemical potential, gravitational potential, or electrical potential. Potential energy is usually given up in some sense and translated to another form of energy by conservation of energy. If we give up electrical potential, we usually use this to accelerate a particle, moving electrons through a wire, moving electrons through an electrical field. So that means we have to have some form of potential difference, which is what we're working towards. But by basic conservation of energy, remember energy can take many forms. It can never be destroyed, it can never be created, merely transferred from one form to another. So, in a mechanic sense, take chemical potential energy in the form of gas, put this into an engine, and burn it in an internal combustion engine, causing pistons to move up and down. We can then translate that energy to a transmission in rotational energy, and then we can translate that to gravitational potential energy by driving up a hill. So all of these are forms of energy, and we could do the calculations here for the enthalpy of this reaction, find out how much energy is generated, how much of that's translated into mechanical energy, and then finally how much is translated into gravitational energy, how much energy is gained by driving up this hill. So we can look at gravitation essentially as a good analog to our electrical potential. When we drop an object, it starts off with gravitational potential energy, mass times gravity times height, and this gravitational potential energy, as an object falls, is converted to kinetic energy. Something like a star is so massive that gravity is always trying to collapse it. Consequently, in a star, we're giving up gravitational potential energy and we're getting radiative energy, heat and light. So in terms of conservation of energy, remember, if we're looking at a gravitational system, if we drop an object, we will start to lose gravitational energy and gain kinetic energy. So at each point in the travel of this safe, its gravitational potential energy is diminishing and its kinetic energy is increasing, until of course its velocity is zero when it hits the floor. But then that energy is expended in terms of mechanical energy, in damaging the floor, in sound, and maybe in light. One of the things we're concerned with when we're looking at potential energy is this a conservative or non-conservative system? And it may have been a while since you looked at mechanics and discussed conservative versus non-conservative forces, and it might be worthwhile going back and taking a look at that, because this will return when we talk about crossed fields in terms of electrical and magnetic systems coinciding. So in a conservative force, this means that work is done in one part of the cycle, as per when we discussed the cycle of thermal engines, and then essentially the opposite is done in the second part of the cycle, producing a zero work system in the end. So here we have a cable car, and if it goes from point 1 to point 2, work is put in against gravity. So we had to put in energy in order to gain gravitational potential energy. All of the gravitational potential energy this cable car has gained on the way up, it will essentially relinquish on the way back down. Therefore, this becomes a conservative system. Remember, in a system like this, don't worry about such things as slack in the bearings of these wheels, or the fact that they squeak, or anything else like that. So in terms of conservative forces, here I decided to give this guy an actual motivation for going to the top of this hill. So here he's going to go from point 1 to point 2. And then the cable car will go back. The cable car has made a round trip and essentially has got zero in terms of work done. So write an equation for U at point 1 and 2. Secondly, write an equation for the total mechanical energy of the system, and then finally calculate the work done by this cable car. Well, the work done by the car will essentially be mgh. The work done by gravity will be negative mgh here. So take the car to the bottom, the work done by gravity is plus mgh, so the total work done by gravity on the car during the round trip is 0 and is independent of the path. So the force of gravity is essentially a conservative force. And we can see similar systems in electrical and magnetic cases where forces are inflicted on particles in a potential field. So if we're still talking about gravity, we're essentially looking at a 1 over r squared force law, which translates well to electricity when you think about Coulomb's law of K Q1 Q2 over r squared. And this gives an inverse first power law for your potential energy function. So the work required to move a test particle, which is m1, from one position to another along some path in a gravitational field, is going to be conservative. So the force on any test particle becomes gmm over r squared. And to overcome that force, you must apply some external force. In doing that, you will apply work. And remember, work is a force times a displacement. So here we're saying the change in the work is negative Fr, which is equal to mgmm over r squared times delta r. Remember, this is simply the force substituted into the work equation. This is the force due to gravity, and this is essentially the displacement. This is a unit vector. So let's talk about electricity after that recap on potential and conservative forces. So potential difference is what we often call voltage, and you'll hear those two terms used interchangeably, either PD, potential difference, or voltage. And this is the reason charge flows from one location to another. And here we're not talking about static electricity, but we're talking about current, moving large amounts of electrons, essentially a river of electrons flowing from one place to another. The kind of thing that's pouring out of the wall right now and powering your computer. And this is the reason charge flows from one location to another. Now, in order to move charge from one place to another, we must have a potential difference. Think about a rolling ball. A rolling ball on the flat surface will essentially go nowhere unless it's actually pushed to its own devices. It will sit stationary. A ball put onto a hill will roll downhill. It goes from large gravitational potential to lower gravitational potential. The same is true of electricity. You must have a voltage difference, a potential difference between two locations to make electrons flow. If we hook a circuit up to a 9-volt battery, then essentially one end of our battery holds the potential at 0, the other end has a potential at 9 volts. So our delta V, our potential difference, would be 9 volts. So voltage is a push that makes electrical charges move, and it's measured in volts. Be careful when you're looking at calculating, say, the speed of a particle. Volts is V, and of course velocity is V, and we will see examples of that case, of that kind. So, in terms of current production, here we have a cell, an electrochemical cell or some other type of battery here, and essentially we have a high potential and a low potential, and electrons will flow through the battery until there's equal amounts of negative charge at both ends of the cell. When this occurs, then you will end up with no more electric current flowing through the system. So once the potentials equalize, your battery is essentially run flat. In terms of current, Current is measured in amps or amperes, which is coulombs per second, how much charge you have passing through a point in your circuit per unit time. Coulombs per second is amps, measure of current. So we have to have a potential difference across our battery in order to make electrons flow. Think of this like water. If we have 2 tanks of water, water will flow from one tank to the other until they reach the same level, at which point they will stop flowing. This is the same with charge. So electrons in motion, as we just defined in the previous slide, but here is the actual hard and fast equation, follow the equation of I equals Q over T. Current equals charge per unit time. Now the electrons must flow through a circuit. They must flow along some conductive pathway. So electrical current flows through conductive paths. If those paths are closed, it's referred to as a circuit. And as we said, batteries are essentially electron pumps. These are the things that set up the potential difference, the voltage change across their terminals. We can then plug in wires or any other components we wish between these terminals and supply electrons to every component in the circuit. There are many different types of batteries. Here's essentially a wet battery where we actually have lead and lead dioxide plates with gels or liquids in between them. And here you have a dry cell where you have a positive and a negative terminal, the kind of thing we see in a lot of different places in most basic equipment like flashlights or radios or anything else which essentially has replaceable batteries. And these usually utilize some kind of paste inside them, which is an electrolytic paste and a carbon rod. So as we said, any of those systems will continue to pump their electrons around a system as long as one end is held at high potential and another at low potential. Electrons will flow from high to low until they are equalized. When the potentials become equal, the system will cease to function and no more current will be transferred. A good example when we talk about potential differences is capacitors. And we're going to talk about capacitors at length sometime in the next section. And a capacitor basically consists of 2 plates, and these plates are connected to a battery, and that will set a potential difference up across the plates. The potential difference will create this electric field. So when connected to the battery, an electric field is set up between these plates. The electric field here is one of those nice and uniform electric fields. And we've said before, the electric field here would be E equals V over D. What is the voltage of the system? So if this was hooked up to a battery, a capacitor always takes the voltage of the battery. Hook it up to a 1.5 volt battery, we would end up with 1.5 volts across the plates. Hook it up to a 9 volt battery, we would end up with 9 volts potential difference across the plates, where E is V over D, the voltage over the separation of the plates. So let's take a quick look at the problem. Here we have a uniform electric field. This is set up by connecting the plates of a parallel plate capacitor to a 12 volt battery. Here's a 12 volt battery, here's our circuit and our wires running to our capacitor. Here's our electric field setup, and that will have the effect of moving electrons and accumulating them across this one plate, leaving a net positive charge on this plate and a net negative charge on this plate. The plates are separated by 0.63 centimeters. What's the magnitude of the electric field in the capacitor? So what is E? So here, an electron will start off on this plate and will be transferred, pushed across here. Remember, this is the negative plate. work must be done here to push electrons to the negative plate. So essentially this battery is providing work to the system to force electrons, negative charge, to accumulate with more negative charge. But here we're looking at the potential. So essentially delta S here is 0.0063. Here we're looking at centimeters, negative 12 volts. If we calculate this, we're going from the negative plate to the positive. E will be delta V by delta S, which will give us 1900 volts per meter. So simple substitution. So let's stop and think about the work that's being done in this case, and of course the kinetic energy of the system. So when work is done on a system, as a recap, this represents the energy transferred into or out of the system. So transferred energy really is work. Delta E, the amount of energy change, equals the work put in or the work coming out. The total energy of the system is usually some combination of potential and kinetic energy. And remember our basic definitions of work. It's a scalar quantity, W here, and is equal to force times a displacement, F times S. And of course that force does not have to be perfectly linear. We could apply force just in the x direction, we would just have F. If we apply our force at any angle, we will have to look at the x and y components of that force. So here, if our displacement was in S, we could only take the F cos theta component of this overall force. So work, remember, is an energy. It's measured in joules. So 1 joule is equal to 1 Newton meter. Force times a distance. Work is equal to Fs. In terms of atomic physics, you often see a slightly more confusing name for a unit, and that is the electron volt. Now, we realize voltage itself is a measure of potential difference, not a unit of work, but they are of course related. And you can often see the electron volt quoted as a unit of work. The reason is that this is the amount of energy you would actually pick up from accelerating an electron through a potential difference of 1 volt. So we can define the electron volt as a unit of work for very small charges, such as moving electrons and protons. And 1 electron volt is 1.6 times 10 to the negative 19 joules. So there's a bit of an odd term here where we're using volts in kind of the wrong context, in that the electron volt is an energy. And that's kind of a historic hang-on. You will have to get used to that, and some questions will ask you to convert joules to electron volts, especially when dealing with particles being accelerated through a field. So when we're looking at work and kinetic energy, we can relate these two together. We can, of course, use kinematics to find velocities and find half mv squared for a moving system. Here we're looking at rearranging v squared equals vi squared plus 2as. And you may have to go back and take a look at some of your basic mechanics in terms of the equations of motion if we're to look, say, at the dynamics of a particle being accelerated in an electrical field. It's essentially a mass put into a potential. So if we can look at kinetic energy, we can relate work and kinetic energy, the kinetic energy of a particle or mass in a field. So work can be Fs, and as we saw when we talked about gravity, we can substitute in here for F and say work therefore will be ma times displacement, mas. It can also be delta E. And in some cases, work can go into changing the velocity of a particle. In that case, keeping mass constant, work would be delta KE, which would be the final kinetic energy minus the initial. Here we'd be looking at changing the voltage. See, I did it. Velocity, VI or VF, either work going in to slow this particle down or to speed it up over some distance s. So that's a bit of a recap of mechanics, and we will be applying some of this. So if it's been a while since you did mechanics, go back and take a look at some of that material. So let's get back on track with electrical potential. So an electrical charge has a field that surrounds it, an electric field. So when a charge moves through an electric field, work must be done. Now remember, with an opposite charge, you'll have to put work in to keep your charges apart. When you're looking at a like charge, you'll have to put work in to keep the charges together. So in the case of our capacitor plate, we were trying to force all of the electrons to accumulate on one plate. That meant pushing negative charge onto an already negatively charged plate, which required us to do quite a lot of work in order to achieve that. An electric force, as per gravity, is conservative. You can look at Coulomb's law, of course, and compare that to gravitation, the gravitational law that was authored by Newton, and you can see that they're pretty much the same form. This means an electric field can store electric potential energy. This means we have to put work in to move Q against an electric field, to move a charge against its electric field. So positive work would be put in. Therefore, the work done by an electric field is given by this equation, which has a negative sign in it. And this is the guiding equation you'll need for looking at the work done by a particle in an electric field. The work is equal to the negative of the charge times E, the electric field strength, times D, which is essentially the distance the particle is moving through the electric field. The change in potential energy here, now be careful here, there's electrical potential, which is voltage, and electrical potential energy, which is the amount of energy that's available to a particle. These are slightly different things. One is a voltage, one is an energy in joules. And the energy in joules, the electrical potential energy, is delta U here, which is equal to negative of the work, which we've seen previously, which is equal to QED, the charge strength multiplied by E multiplied by how far the particle's moving, its displacement. So please be aware of the difference between electrical potential energy and electrical potential outright. That's a very common error that's made, especially on exams. So recall Coulomb's law. F here was K Q1 Q2 over R squared, and that gave us the force on an electrical charge. And we had these equations that we defined when we first started talking about electrical systems. And this was stating that the electric field strength E is equal to V over D, a voltage over a separation, which is equal to F over Q, or K Q over R squared. And these will be your guiding equations in relating electric field to voltage. You will, of course, have other equations you can actually substitute in to get maybe V or F, and then substitute into E. So, in terms of electrical potential, let's take a look at how we define that. Well, this is a change in voltage here. So this is a change in V, delta V. So here we're not talking about speed, here we're talking about voltage. And that's equal to delta U over Q. How much energy is changed, how much of an energy change divided by your charge, which will also be negative of the work over Q. Of course, the volt, therefore, becomes a joule in energy per coulomb of charge. How much energy are you getting out of a system per coulomb? The volt. And of course, as we mentioned before, the electron volt can also, by that reckoning, become a unit of energy. So 1 electron volt essentially is the charge on the electron using this equation, how much work was done to accelerate an electron through a voltage of 1 volt. So we take 1.6 times 10 to the negative 19, the fundamental charge of the electron, and of course a proton, and multiply it by 1 volt, we'll get 1.6 times 10 to the negative 19 joules. So our voltage can also be written as PD, potential difference. And the potential difference, if for 1 joule to move 1 coulomb of charge, is 1 volt. So a volt is the potential difference between 2 points. The electrical potential is work over charge, which PD is W over Q. So voltage can be thought of as essentially the energy transferred per coulomb of electrical charge. So when we're looking at transferring energy, we essentially have, as I said, the analog between gravity and charges. So in our gravitational field, we could take a particle and we could put it in the gravitational field of the Earth, and that particle mass of m would experience a force equal to mg. F equals ma. A is the acceleration due to gravity, so force equals the mg here. In terms of our electrical field here, our force would be equal to Q times E. How much charge multiplied by the electrical field, E. Now, here's a slight oddity in terms of the electrical system versus the gravitational system. The gravitational system is always attractive. You will not have repulsive gravity, where this mass will fly off into space and repel against the Earth's field, which would be useful because then we could go into space for cheap, but it doesn't work that way. Gravity essentially has a very much more complicated polar relationship that we still haven't fathomed. Electricity is essentially positive or negative in charge. So here our electrical charge, if it were negative, the whole system would be reversed and this particle would accelerate in the opposite direction. So electrical potential equals the potential energy per unit charge, V is U over Q. That means our potential difference, delta V, was delta U over Q0, which was work over Q. But we can also say if our potential energy is essentially at infinity, very, very far away in this field, then the voltage becomes work over Q. So here delta V is work over Q, or we can say the voltage becomes work over Q. So in terms of potential energy, we can define things in terms of an electrical potential energy, or we can define things in terms of, say, a change in kinetic energy. If we have a field working on a particle, then that means it's going to change in speed. It could slow down, it could speed up, but still we're looking at a change in velocity, which means we have to look at kinetic energy, half mv squared. So delta E is equal to the final kinetic energy minus the initial, or is equal to the applied work plus the work done by the field on the particle. If a particle is stationary before and after it's moved, then the applied work is essentially negative W. Or we could say from delta U equals the change in potential energy is equal to the applied work, work becomes Q delta V. How much of a voltage did you move your particle through times its charge? And we've essentially already defined this. But here I did want to mention that 1 volt is 1 joule per coulomb. Remember, this is 1 Newton meter per coulomb. So if we say 1 volt per meter here is essentially equal to 1 Newton per Coulomb. This is the definition of our electric field E. And this is where the electron volt becomes very useful when we're looking at charged particles, because the electron volt is usually the kinetic energy acquired by moving our charge. Now the reason I mention this is quite often we're looking at particles placed between capacitor plates. 1 electron volt is the kinetic energy acquired by moving a charge of plus E through 1 volt. The electric field lines point in the direction of decreasing electrical potential from positive to negative. A positively charged particle will accelerate in the direction of the electric field and increase its kinetic energy as its electrical potential energy decreases. So we're always exchanging energy, potential to kinetic or kinetic to potential, essentially going uphill or downhill in terms of our electric field. So electric field lines point in the direction of decreasing electric potential. So you should be able to look at this particular field map between these two particles and say this is at high potential, this end is at low potential. A positively charged particle will follow the electric field lines and increase its kinetic energy as potential energy decreases. High potential, low potential. Positive particle thrown into this system will end up increasing its kinetic energy, increasing its velocity, but reducing its potential energy. Throw a negative charge in here and it'll do the opposite. It'll go this way through the field, giving up potential energy the opposite way and gaining kinetic energy. So as we said, potential difference is the reason that electrical charge flows from one place to another, and that's essentially the voltage, the push that makes the electric charges move. And of course, in a conservative field, delta U becomes Fs, where we can substitute in for F as QE times delta S. So this is just a substitution for F here. So the change in potential energy per unit charge is our potential difference, or V or delta V can be delta U over Q or E delta S. So essentially our change in velocity here for a moving particle can be the electrical field strength times the displacement. So that means our change in potential energy is this. That means our change in voltage becomes, as we just saw, this. Change in velocity is E delta S. The only change in potential energy is important. So only the change in PE, delta PE, counts. So that's the only place where essentially potential energy is given up and velocity increases. V's here, these sort of V's in this case, are velocity. So the electrical potential is a continuous function except where a charge is located. So let's look at that in a realistic sense. Here we have an electric field set up between two plates. The electric potential on this plate will be high and fall off linearly with distance. So electric field is delta V, the voltage, divided by delta S. Positive, negative. So the electric potential energy, as we said previously, is U equals QV in units of joules. If we look at the potential of a point charge, we can actually map this out in 3 dimensions. And looking at potential graphs can actually be quite useful. But if we take just an electron or a proton or something like that, we can actually map it in 3 dimensions. So if we put a particle here on our point charge, it will roll essentially downhill, high voltage to low voltage. If we put work in, we can force our particle to go up into this potential. So this is what we mean by a potential in a graphical sense. So if we actually look at potential, we can say that we have points A and B, and we have our charge Q. If we wanted to look at the potential due to this charge at 2 locations, we could say here that we would say the sum of the voltages in this system would end up giving us our total potential. So here V is equal to 1 over 4 pi epsilon 0, remember this is essentially K, times Q over R. We can take Q out of here. This is the useful way of actually expressing K in this sense. Then we can say the difference in potential, this is voltage at A versus voltage at B, delta V, will be Q over 4 pi epsilon 0 times 1 over D1 minus 1 over D2. And this is a very useful trick if we're looking at the change in potential from 2 positions. You could, of course, compute V for one location, V for the other, and then simply take the difference. So the electrical potential for point charges separated by some distance r will be kq over r. And remember, this will be in units of volts, or joules per coulomb if you choose to deconstruct your volt. Let's take a look at a problem here. What's the electric potential at distance of r equals 0.529 times 10 to the minus 10 meters from a proton? Well, V is equal to kq over r, where q is essentially the charge on the electron, but positive. So ke over r. Substitute in, this will become 8.99 times 10 to the 9. This is our constant, K of course, Coulomb's constant, times 1.6 times 10 to the minus 19 coulombs. Divide this by R. This is essentially the very small distance, atomic level distance, so 0.529 times 10 to the minus 10 meters, and we'll end up with 27.2 joules per coulomb. Remember, voltage is a very common unit, so it doesn't hurt to convert this to volts. So 27.2 volts between these 2 positions, 0.529 times 10 to the minus 10 meters apart away from a proton. So what would be the potential energy if we have now 2 charged particles, an electron and a proton at this separation? Well, U, the actual potential energy, is Q, the charge, times the potential difference, V. So this would essentially be E times V. Negative E, the charge on the electron, times 27.2 volts. This will actually give us a negative value of 27.2 electron volts. So when we're talking about electric potential energy, here is our 2 plates. And essentially we're holding one plate with positive charge and then putting work into the system, or at least a battery is putting work into the system to push electrons onto this plate and accumulate negative charge on this side. That means if we let an electron go in our electric field, it would naturally want to gravitate towards the positive plate, and the proton, the plus charge here, would want to gravitate towards the negative plate. They would spontaneously, left alone, go towards their opposite charges. Let's take a look at the kinetic energy of an electron in an electric field. So an electron starts out from rest at a point in space at which the electrical potential is 9 volts. If the only force on this electron comes from the electrical potential, how fast will the electron be moving if it passes through a second point in space where the potential is 10 volts? So the potential difference here is obvious, of 1 volt. So the electrical potential is 9 volts. How fast is the electron moving as it passes through the point in space where V is 10? So let's take a look at this in terms of work and kinetic energy. So work is equal to potential energy plus kinetic energy. As work here is equal to 0 in this particular case, because kinetic and potential energy must balance, delta K is positive if the electron speeds up. So this means delta U must be negative. As the charge on the electron is also negative, this means delta U, by our equations, becomes Q delta V. Q is the negative charge on the electron times the change in voltage. This means we will end up with an overall -1 electron volt as our potential energy. Remember, the electron volt is indeed an energy in itself. Our delta V is positive, the charge on the electron is negative, giving a -1 eV. This still does not solve our problem. So we just said that delta U was -E delta V, which gives us -1 electron volt. This means delta KE is negative delta U, which means the kinetic energy was +1 electron volts. So if our electron has 1 eV of kinetic energy, we need to find its speed. 1 eV is equal to 1.6 times 10 to the -19 joules. This is one of our standard values. The change in kinetic energy will be half mv squared, as the kinetic energy is 0 at the 9 volt point and some non-zero value at 10. We now know what the kinetic energy is, and we also know what the mass of an electron is from our standard values. Therefore, we can say that the velocity at point 2 is going to be the square root of 2 delta Ke over m. Substituting in for our electron volt, and then we can divide by the mass of the electron. Let's take the root, and we'll end up with 5.9 times 10 to the 5 meters per second. So let's look at a situation where a proton and an electron are placed in our constant electric field between our capacitor plates. What happens if we release a proton from the positive side and an electron from the negative side? Which will have the larger acceleration? So remember, the electron is going to start off at the negative plate and be attracted to the positive side. The proton will start off at the positive plate and be attracted to the negative side. So the proton will travel the same distance from here to here as the electron travels from here to here. The electron moving against the field essentially, and the proton moving with the field. So which will have the larger acceleration? No, enough of that. Anyway, so which one will have the larger acceleration? Well, based on our electrical equations, of course, the same amount of energy will be imparted to the electron as imparted to the proton, because essentially the force is going to be due to the charge, F equals QE. The amount of work put in will depend on the charge, and the charge on the proton and the electron is identical. There is a difference though, that the electron has a much smaller mass than the proton. If we equate our field equations to F equals ma, that means that in order to have the same force stay the same on both the electron and the proton, because the same electrical force will be given to the electron and the proton, when we translate this to F equals ma, the acceleration of the electron will end up being larger than the acceleration of the proton. So the electron will have the larger acceleration in this case. Although their charges are the same, the mass of the electron is much smaller than the proton. And we can always go back to mechanics and equate our electrical force to F equals ma in that fashion. So if we have a mass moving from point A to point B due to any conservative force, we can look at our mix of half mv squared kinetic energy and potential energy. And we can say half mv squared at A plus the potential energy at A will end up being half mv squared at B plus the potential energy at B. So the actual proportions here will change. The potential to kinetic proportion on this side of the equation will change, but these equations will balance in terms of the amount of joules on both sides. So for an electrical force, U equals QV. So if we look at our conservation of energy, the same as we would in mechanics, we could easily have gravitational potential here. Here we're looking at electrical potential. We can substitute QV in here, giving us half mvb squared equaling half mva squared plus the difference in our potential energy. How much potential energy was either gained or given up by this system. That will essentially give us half mva squared q times va minus vb. So remember U here is QV. Substituting in will give us a handy equation to determine the kinetic energy of a particle between 2 points. And always remember in a situation like this, the force on a negative charge is opposite to the field direction. A positive charge accelerates in the direction of decreasing electric potential, a negative charge accelerates in the direction of increasing electric potential. But in both cases, Q, the charge, moves to a region of lower potential energy relative to that charge. Just the negative, just everything opposite to the positive. So, a proton and an electron are in a constant electric field created by oppositely charged plates. The proton is released from the positive side again, and the electron from the negative side. When it strikes the opposite plate, which has more kinetic energy? So the electron's going this way, proton's going this way, both the same fundamental charge, remember. Which one is going to strike the plate with the most kinetic energy? And here are your options. Proton, electron, both of them acquire the same, neither, because there's no change in kinetic energy, or both acquire the same kinetic energy, but with opposite signs. I'm not going to sing this time. Turns out that both of them will acquire an identical kinetic energy. So U here will be QV. The proton and the electron will have the same magnitude charge. This is the potential energy by the electric field. Both will have the same initial electrical potential energy. But as energy is conserved, they both have the same kinetic energy after they reach the opposite plate. So when we're talking about potentials, we saw this for the point charge previously, the electrical potential can be viewed in this sense. And you can see these for gravitational cases now as well as electrical cases. But essentially, when we're looking at the positive case, we're looking at an identical potential to the negative case, just one goes upwards, the other goes downwards. And in a two-dimensional sense, they tend to get expressed this way, which is a little easier to visualize rather than the distortion of a field in 4 dimensions. So here we have two particles lying on the x-axis, positive q, negative 2q. So here we have an increasing potential here due to the positive Q, and a negative potential due to the negative 2Q, which of course is much deeper because that has twice the charge as the positive. So our electrical potential, as we said before, is QV or K, Q1, Q2 over R if you have the separation. And this is something you should have seen before in terms of the force due to gravity and the potential energy due to gravity. You would have seen GMM over R squared for its force and its gravitational potential being given by GMM over R. This is the same. So in terms of electrical systems, U will be QK, Q1, Q2 over R. This is not an error. I have not missed a squared out here. We are not expressing a force here. We're expressing a potential energy. So please be aware of that. So when we're looking at the electrical potential of point charges, we can essentially say that this charge, positive Q, will have some electrical potential. And we can determine that for any particular point. So here we could determine the potential for a test charge introduced at point A. In this case, if these are both positive, we would have an overall potential which would result in a repulsive force. So this particle would end up with its potential going essentially diminishing and its velocity increasing. So the difference in potential energy between point A and point B here would be U at point A minus U at point B. So the potential due to this charge is going to diminish as essentially as 1 over R here. So UA, potential at A, minus the potential energy at B becomes K Q1 or Q0 times the original Q over RA minus the same two charges times K over RB. And that's the amount of potential energy change between two locations. Or of course, VA minus VB could be 1 over Q. So just as a quick recap here, if we're looking at work and potential energy, which group of charges in this case took more work to bring together from some very large distance? So essentially bringing these particles from infinity and forcing them into the same space. Which group of charges would have taken more work to bring together? And here we have two particles on the x-axis, a positive 2 and a positive 1 charge, and they've been essentially forced together to some distance d. Here we have essentially the same amount of charge, positive 1, positive 1, positive 1, but here they are arranged in an equilateral triangle. So which one would take more work, A, B, or would they both take the same amount of work? Again, I'm not going to sing. It's B. So the work needed to assemble a collection of charges is the same as the total potential energy of those charges. In this particular case, for one pair, we're going to apply U, which I've shown as PE here just because we're discussing potential energy. U as potential energy would be K Q1 Q2 over R. This would essentially be done for the single pair for the first case on the x-axis. So the potential energy would be K 2 times 1 over their separation, giving you an overall answer of K 2 over D. In the second case for the triangle, what we've essentially got is three particles that we're bringing together. So we'd end up with 3K 1 times 1 over D. So we would have to look at each pair individually and end up with 3K 1 over D. Meaning that our situation would require more potential energy here than here. And that's essentially what our potentials are showing. And we have seen this slide a couple of times before, but when we are talking about potential lines and essentially changes in potential, we can define what we call an equipotential surface. So if you look at this particular slide once again, you can see lines, rings running around this potential. Any one of these red lines here are referred to as equipotential lines. It wouldn't matter where you were on this line, the potential would always be the same. So here we're at about 10. If we stayed on any part of this line on this 10 ring, we would be at 10 volts. The same here. Here we're looking at a situation where this is 0 volts. Any part of this line would be 0 volts. So you can kind of compare this to, say, equipotential surfaces on, say, a mountain. Here's a mountain in terms of gravitational potential energy, and here it's been separated into contours. So looking at the mountain from above, here's an elevation of 450 feet essentially, here's an elevation of 100. Anywhere on this particular color, we'd be at 400. Anywhere on this particular color, we'd be at 300. These are all the same height, and of course those heights, if we used mass times gravity times height, would translate to a constant potential energy anywhere on this particular elevation. And that's what you should see essentially here. Anywhere at one particular potential, we can define an equipotential line for a nicely symmetric system. And that's really what we were showing here, was these changes in potential. And we can algebraically sum those potentials should we need. So if we look at a dipole, a positive and a negative charge here, we're looking at our electric field being these sort of turquoise lines running from the positive to the negative charge. But then we have another series of lines, these circular potential lines. So in a dipolar field, this would essentially be one single potential anywhere on this circle. Again, anywhere on this circle, another equipotential line. In the center, we'll have these lines running through here, essentially our equipotentials for any point along this particular electric field. So don't mix these up. Here you have an electric field and you have the potential field, which is these purple lines. And these are all equipotential lines. If this is 12 volts, any point on this line will be 12 volts. And there's that same dipole field seen in a three-dimensional setting. So electric potential and electric field essentially have a very similar relationship here. Here again we've got an electric field due to a positive charge, so radiating outwards, and we have our equipotential lines. As you can see, the closer the field lines get together, the closer the equipotential lines get together. So potentials varying much more quickly, much more confined space here than it is out here. So those lines in that 2D sense show surfaces of constant potential. And we saw that previously when we were looking at essentially attractive cases, positive and negative, but for point charges which are repulsive, you'll see essentially these figure of 8 kind of potentials. So here the potentials essentially butting against one another. Here the potentials for a repulsive field actually meld together. So this means if we wanted to, say, contain a charged particle, we could set up an electric field between these two repulsive charges and drop our test charge in here, and it would essentially go round and round and round in this equipotential field for as long as we would want to do it. And this is a method that we can use to trap charged particles for study in accelerators and equipment such as that. So when we talk about conductors, which is something we're going to talk about in a bit more detail, an ideal conductor is essentially an equipotential surface. If two conductors are held at the same potential, the one with more of a curve, or remember as we said before about conductors, a more pointy one, will have a larger electrical field around it. That's also true for different parts of the same conductor. So two conductors at the same potential, as we said, the more curved, will have the larger electric field. These two are at the same potential, V. Here's a radius of r, here's a radius of r over 2. Essentially what will happen here is the low charge density here will give you a lower electric field. This curve is essentially more extreme due to the smaller radius, r here and r over 2 here. At the smaller radius, you'll end up with a higher concentration of electric field and therefore a higher charge density. So reduce the radius, increase the curvature, end up with a greater electric field. And where are these used? Well, this can pop up in a lot of places, but of course something like inside a human body, a heart actually uses a propagation of an electrical impulse across it, and looking at equipotential surfaces can help us see how atrial depolarization and repolarization of ventricles can occur. Increasingly, people are looking at interfacing the human brain to equipment, and this guy looks extremely relaxed having his head hooked up to a machine, and looking at an EEG can essentially measure brain activity. Of course, when we're looking at an EEG as opposed to an EKG, if we're looking at a heart, an EEG uses microvolts here. So this is 10 to the negative 6 volts that we're seeing. So we're talking about very, very small electrical potentials when we're looking at an EEG.